Robot Talk is the podcast that sits down with roboticists from around the world and asks them the questions you always wanted answered. Like, do robot hands need 5 digits? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week we're returning to the topic of robot dexterity with a guest who's been working at the forefront of innovation in robotic hands and grippers for over 20 years. Before we get started, don't forget to support the podcast by signing up as a paid supporter on Patreon. Not only will you receive my eternal gratitude for helping the podcast to continue, but you'll also get access to lots of cool perks, including monthly bonus episodes, behind-the-scenes updates, merch discounts, and more. Check out patreon.com/Claire Asher and join the Robot Talk community today. So, without further ado, it's time for me to introduce this week's guest. I recently had a fun chat with Rich Walker from Shadow Robot Company about their advanced robotic hands for research and industry. Today, I'm chatting to Rich Walker, Director of Shadow Robot, a company building next-generation Dexterous robot hands. Hi Rich, I'm excited to have you on Robot Talk.
Hi Claire, thank you for the invitation. Pleasure to be here.
So, as I understand it, Shadow Robot has a bit of an unusual backstory compared to most robotics companies. So, to get us started, can you tell us a bit about how the company was founded and what originally motivated you to work on robotic hands?
Sure. So we actually started out in the 1980s as a group of people having fun building robots. We're literally the classic kind of hobbyists working out of someone's attic. The guy who set up the group, a man named Richard Greenhill, he was by trade a photographer, and he got excited by the potential of the home computer. And he thought, how much more exciting could these be if they could do things, act in the world? So he started building robots because he just felt he ought to. And he kind of gathered together a critical mass of people who were interested. And we did that for some years. And then in 1997, we got offered a piece of engineering work from another company. And they were like, but we can't give you the engineering work unless you have a company to take the contract.
Right.
So we're like, okay, we'll set up a company. And that's how we started setting up a company. Before that, we did all sorts of interesting things with robot technology. So we were very interested in what's now called soft actuation, pneumatic muscles. We built a whole bunch of interesting things there, including one of the world's first bipeds, which is now in the permanent collection of the Science Museum, next to the Honda HRP1, which was the next generation of biped. And Honda came out with that in the mid-90s, having spent a huge amount of money developing a really, really super top technology biped, which was kind of a little bit depressing because we'd done it as hobbyists with what we could scrape together. And they'd done it out of their marketing budget. And we kind of went, okay, maybe we'll do something different, which is when we took a kind of sharp turn to the right and started building hands.
It's funny that you mentioned that robot in the Science Museum because actually I was going to ask you about this because last summer I hosted a panel discussion at the Great Exhibition Road Festival on humanoids, and one of the panelists was Ben Russell from the Science Museum.
He's a great guy.
And he told us this story of how he got called up by a company called Shadow Robot who said, oh, we've got a humanoid in the basement. Do you want to come and have a look at it? And then he showed us the photos. So, yeah, I had to mention it to you.
Did he show you the photo of crawling through our crawl space to where we'd stashed the biped?
He showed a picture of basically like half of a bipedal robot sort of sticking out of floorboards. And I couldn't make head nor tail of the picture until he kind of explained it.
We had a weird space under some stairs. You know, one of those kind of like understair cupboards that just keeps going back and back and back. And it's one of those. And we'd just been stuffing things into it that were obsolete robots. Didn't want to throw them away because you never knew when the lead mechanical engineering curator from the Science Museum might decide to come out and have a crawl through your cupboards. Yeah. But no, he was very pleased to find it. And we were very pleased when he absolutely insisted that he couldn't accept it as a loan. It had to be a permanent donation to the museum. And we said, wait, does that mean that you will never give it back to us? And he said, yes. And we said, great, we'll go with that. Yeah.
Yeah, amazing. I love this story.
Yes.
So, coming back to robot hands, Shadow Robot produces a variety of different robot hands that have different features and different applications. So can you kind of give us a bit of an overview of the different robot hands that you produce?
Sure. We're known for kind of two main categories, I guess, of robot hands. There's the classic, we refer to it as a classic because we're terrible at thinking of names, anthropomorphic hand, designed when we built it to look as much like a human hand as possible in terms of scale, in terms of range of movement, in terms of ability. And that was developed essentially from the ground up to be as close as we could get to human form factor and then try to make it work on top of that. So I did that in 2003, 2004, 2005. So very, very advanced at the time. Originally built with pneumatics, compressed air muscles, and later we shifted it over to using a motor technique we developed ourselves. And that we made because we wanted it, and we had people who were in the research space who said, we would like this as well, and we're willing to pay you for these because we want to use it to do our R&D in robotics. And so for many years, it was kind of the gold standard for doing research in robotics. What do you want to do your R&D? You want a shadow hand. Then about 7 or 8 years ago, Google DeepMind came to us and said, look, we've seen some really interesting R&D done with this hardware, great hardware. The only drawback with it is people keep breaking it. And we said, yeah. That's why we have a service agreement and repair and maintenance and really fast support and so on. I said, yeah, we get that. We appreciate that. We've used that. But we're wondering if you could build us a robot hand that wouldn't break. And we thought, well, that's an interesting challenge. And we kind of stared at it for a while and we said, what do you want to do with it? And they said, well, we're machine learning people. We want to do machine learning. We want to have a robot that can interact with things in the real world all the time. And we said, okay, so it's got to be able to crash into things, got to be able to collide. It's got to be able to generate huge amounts of data for machine learning. It's got to be really, really dexterous in terms of its range of movements and the sensitivity of those movements. I said, does it have to be human-like? And they sort of stared for a minute and they were like, no. So we built this non-anthropomorphic hand, and it's super dexterous, it's super flexible, it's super capable, it's super, super robust. We have video of sort of hitting it with hammers and things, just like casually. We did thousands of hours of hitting that robot to make sure it really was super robust. It's just not human-like. It has sort of typically 3 or 4 fingers. They're quite big and chunky fingers, but they're hugely sensitive and hugely dexterous. And there's some lovely videos from Google DeepMind of them doing really quite complex manipulation tasks with this, where they're scrabbling with an object on the table and kind of scraping the table and flicking the object. And if you zoom in, you can see the wear on the table where the robot has worn out the table.
Amazing. Yeah, I'm really interested in this kind of anthropomorphic versus not for hands because my background is in evolutionary biology, and basically all mammals have some form of a 5-fingered hand. But as I understand it, the general consensus among evolutionary biologists is that is somewhat of an accident. The ancestor of all mammals had 5 fingers. Obviously that worked. And so everything else kind of ended up with a version of that. Where do you stand on how many fingers you need and the kind of the pros and cons of different approaches?
Well, that makes sense. And I think it's kind of like a just so story for robotics, isn't it? It's why is 5 fingers just so? Because that's how it is. We spent a lot of time asking people questions about this. And so far we found one person who could definitively say, in my industry, you have to have all your fingers, 4 fingers and a thumb on each hand.
Yeah.
And that was someone who worked in biosafety level 3 and 4.
Okay.
Where one of the kind of tasks you perform is to take a sample vial, unscrew the top of the sample vial, take the lid off with 2 of your fingers, and then pick up a tool and use the tool on the sample, put the tool down again, and then put the lid back on. And you're not putting the lid down because if you touch something, you cross-contaminated, and you don't want to do that at BSL 3 or 4. It's really, really bad. Yeah. So there, they very definitely like, we like to have all of our fingers in this industry. There is some interesting research from Etienne Badet and colleagues at Imperial College where they found people with extra fingers and they studied what they do with the extra fingers. And essentially, a lot of the time we use our 3 fingers as a kind of tripod grasp, tripod manipulator.
Yeah.
So people with 6 fingers basically can do 2 tripods at the same time. which is kind of interesting.
Yeah.
We haven't yet built a 6-fingered robot, but maybe one day.
Yeah, that would be cool. So you mentioned like the use of your robotic hands in research. Is that the kind of the main clients that you sell your robotic hands to?
Historically, yeah. We joke all our customers have the same first name. If they're over 40, they're called Professor something. They might be in industry, but if they are, they've got a professorship on the side somewhere. Because essentially what we're dealing with is people who are innovating in robotics or using robotics, and they want dexterity. They don't quite know what they want to do yet. They might have a broad idea. And if you have a broad idea, you don't want to be limited by the capability of the hardware. So a shadow hand gives you as wide a range of possibilities as you can get. Use that. And then when you work out what you actually want, you can build a specific thing that you want at that point. So we do quite a lot of kind of, I guess you could call them innovation engagements, where someone comes in and goes, our business is in cooking and we want to use robots in cooking. And we're like, okay, let's start you with a human-like robot hands and arms and see what you can do with that. And once you've understood what the cooking problem you want to solve is, then you can work out how to build a robot that can do that cooking problem. And they go away and they raise their investment money, either super demo to their board or whatever to make that happen.
Okay. So what do you think are the biggest outstanding challenges in terms of robot dexterity? I'm hearing robot dexterity everywhere at the moment. Everyone's talking about it. It's a very kind of hot topic. Where do you think the field will go next?
Well, I mean, the biggest problem is defining it.
Yeah.
If you get 3 or 4 roboticists together, give us a beer each and leave us for half an hour and we'll start arguing about this. Give us 3 beers and we'll be really, really vehemently into the argument about it. And somebody will be trying to do coin tricks and somebody else will be trying to flip their pen and somebody will be arguing about surgery. And because we don't have a good functional definition that we can use. And even when you talk to people for whom dexterity is a super important ability for them, they don't either. So you talk to surgeons and surgeons talk about dexterity. And then you say, well, what's the difference between a surgeon who can tie a suture and a surgeon who can tie a suture using a Da Vinci robot? And they're like, yeah, well, it's different, actually. Yeah, it's kind of, you can do a little bit more of this, a little bit less of that. You talk to people who do close-up magic and you ask them and the answer is practice. That's the difference, is just practice. So it's kind of interesting because it's something that we very much do, we very much know, but it's kind of like, if you ask a fish about water, it doesn't see water, it swims. If you ask a human about dexterity, well, it's what we do.
Yeah. And actually that's a theme that comes up in a lot of my conversations with roboticists, is that the things that are really difficult in robotics are the things that we just take for granted, that we think are so easy we don't even realize we're doing them.
Yeah, it's originally Moravec's paradox, I think, as Moravec was the first person to point out that actually the stuff that we thought was clever was actually very, very systematic and easy for machines to do, like playing chess. The stuff that we thought was easy, famously the Dartmouth workshop, where they decided that they'd solve vision on computers. A couple of postdocs would spend the summer solve it. And that was in the 1950s. And we're still difficult. It's still difficult.
Yeah. So you've mentioned various different ways that robot hands move, right? You've mentioned like pneumatics and the kind of more bio-inspired kind of muscle approach. Do you think that is key to dexterity, putting aside the fact that we can't define what dexterity is?
I think the thing about robot arms and hands is that the hand is at the end of the arm, and that therefore means that all of the actuation in the arm is spent keeping the hand in place and then giving it the ability to do something. So whatever the payload that you've got on the arm, you've got weight of the hand and then what you want to do with that hand. So the more weight you put at the end of the arm, the stronger the arm needs to be, the less safe the system is, the harder it is to make small, precise movements with it, and so on.
Yeah.
So one goal with hand design, with manipulator design, is to keep the weight down as much as possible. And that comes down normally to an actuator problem. I could get very, very precise, powerful actuators, but they're heavy.
Yeah.
So if I want something that's lightweight, I have to use actuators that are correspondingly lightweight, and therefore I'm making trade-offs. I can't use certain types of drive technology. I can't use certain types of control technology. Those trade-offs are not the end of the world. They're just, engineering is all about trade-offs. It's all about saying, well, I'll take a bit of that and a bit of that and compromise, but that lets me do this with it. What we've seen over the period we've been working is that lots and lots of people are trying to think of new types of actuator. And it's the classic disruptive innovation problem. You're chasing brushless DC motors, which are really, really good. The rare earth permanent magnet motor, really, really high performance. And if you're trying to compete in that space, you've got 150 years of motor development to catch up on. If, however, you can make something that operates in a different space to the space the motor can operate in, then suddenly the fact that you're nothing like as performative as the motor isn't a handicap, it's just a difference, but you can do something that the motor couldn't do. So that might be working in a material choice where you can't possibly build a motor out of that material, or that might be working with a structure which you don't have the space to put a motor, but you can have the structure change shape by itself, soft actuation. Or it might be that you can get some other property in the actuator that a motor couldn't do very well at. So that's the kind of trade-off space.
Yeah. How much inspiration do you take from nature? Because a lot of animals use kind of muscles, but there are all kinds of other ways of doing things if you start looking at like starfish and jellyfish and the weird stuff in the ocean.
The weirdness of nature is an endless source of both inspiration and sometimes horror. And when you look at how biological structures are designed, I say designed, exist, work, and are tuned and optimized, it's not what you think of as an engineer because you can't constrain it and make guarantees about it.
Yeah.
It's this resulted in a behavior that works, and it works well enough that the system works well enough to exist and continue to exist. And you can't make functional guarantees about starfish. You can't even make functional guarantees about a human. So there's some great results from the early period of evolutionary algorithms in computing in the 1980s and 90s when the University of Sussex researchers were doing evolving circuits on gate array type chips. And they found that when they looked at what the circuit was doing, they were like, we don't understand how this works. Like the logic doesn't make sense. There's no way that this logic can be doing what is happening. And when they took the actual bit stream and talked to the chip designers, they said, what's going on here? And the chip designers were like, this is wrong. You shouldn't turn on those two gates at the same time, because if you do, you'll basically short the power supply in that region and turn off this bit over here. And they were like, turn off that bit over there. Yeah. It had learned a way to basically modulate another part of the chip effectively through the power substrate. Made absolutely no sense in terms of the logic. You would not design something like that. But weirdly, kind of similar to the way hormones operate on the brain. You trigger a hormone somewhere and it modulates the entire pattern of behavior elsewhere in the system.
Yeah.
So I don't know. Biology gets to use these hacks. Well, they're not hacks necessarily, they're techniques. As engineers, because we want to say, we can tell you what this will do and we can predict what it will do and we can give you a reliability, then we find it hard to use those kind of tricks.
Yeah, that's a shame.
Although some of them might be usable. There might be ways to take those techniques and bring them across and use them. And certainly there are ways to be inspired by them. So yeah, we don't have things like self-lubricating joints. The human knuckle generates fluids that lubricate itself and it will regrow. Can't do that in engineering, which is a great shame. I really like that.
Yeah. So we had an audience question from Anil, which was submitted on the website. Anil says, how do you see soft robotics developing? What are the bottlenecks in current soft robotics, specifically focused on robot dexterity?
Soft robotics is a really, really interesting area. We technically started out in that. We were building things using soft pneumatic actuation before it was really called soft robotics. And the challenge was always in control. You could make a thing which behaved well, but you couldn't do precise control with it.
Yeah.
Now, that's not necessarily a disadvantage. If you know the problem you want to solve and you can generate a soft structure that does that, that's what the morphology creates in the world, then it can be absolutely perfect for that. And there are some fantastic soft grasping tools and gripping tools that do exactly this. There's some really interesting research going on at the moment in essentially how do we build simulation tools and modeling tools to give soft robotics the control rigor that classical mechanical engineering and control theory has. We don't know whether they'll work or not, but it's a really, really interesting area. So I'd say that's kind of one of the super cool challenges is actually, is it possible to use a stupid amount of compute over here to turn a soft morphology into something with actually reliable and predictable behavior, and then not use a super huge amount of compute, but just have the thing work and work well? That would be, I think, really exciting.
Yeah. If I think about soft robotics and I think about dexterity, what immediately springs to my mind, coming back to the bio-inspired stuff, is octopuses.
Yeah.
If you could come up with, a robotic gripper that has the precision and the dexterity of an octopus arm, And also, they are controlled independently from the brain. Like that to me seems like the gold standard.
They're controlled independently from the brain. And as I understand it, one arm can learn a skill and transfer that skill to the other arms without it going through the brain, which seems kind of baffling and very, very impressive. We actually, many years ago, we did a European research project, which was starting with the way octopi worked and trying to transfer that through into surgical robotics, which was super interesting until you try and not Google for images around octopuses and surgical robotics and things. Don't do that.
No.
But that was actually looking at exactly that. How can you take ideas inspired by the octopus arm and say, okay, can we use those to do endoscopic and natural orifice transluminal endoscopy type techniques? Really, really interesting project. It's hard to look up because it was in the way of all European projects. It had a stupid acronym. It was called Stiff Flop.
Oh, no.
Exactly.
Yeah, I'm not Googling that.
No, it's but really good work, actually. Really good work.
I think trying to convince people to be operated on by a robot octopus might be quite a hard sell as well.
It's interesting. When we were doing that project, we talked a lot to people who were in the space of moving from traditional surgery through to laparoscopic surgery and then looking at kind of robotic-assisted surgery, the Da Vinci type systems. And they said there was a massive interest in having Da Vinci robots in hospitals where patients got to choose the hospital.
Okay.
Because for men of a certain age, a prostatectomy is not an uncommon procedure. And a prostatectomy done with a robot surgeon, or rather with a Da Vinci system, which is kind of robotic, not an autonomous robot doing it.
It's teleoperated.
Was seen as a safer procedure.
Okay.
There's less likelihood that you would have a catastrophic problem that would lead to a long-term problem. Actually, the figures weren't much different. A competent laparoscopic surgeon and a competent Da Vinci surgeon had pretty much the same results in terms of the procedure itself, but the word had got out. So among people who were choosing where to have their surgical procedure, they wanted to know the hospital had a Da Vinci system. So quite a few of them were just in the lobby.
That's really interesting. We had a second audience question. This was from Elodie on Twitter, who says, what is the connector standard situation? Half of my time modding hardware is getting mismatched boards to talk to each other. Specs matter more than marketing.
Yep. Yep. Cables and connectors, those are the two biggest problems in robotics when you ignore all the other ones about actuators and tendons. It's really interesting how people are prone to saying, obviously, this is a standard interface, and it's just like it's their version of a standard interface. Even things like, USB, as we all know, has spawned a proliferation of variants, most of which are relatively compatible with each other at some level, but not super compatible at the lowest possible level. And don't even get started on the high speed. Is it USB 3.1, 3.2, 3.2 SS? It is the problem if you're trying to reuse components or subsystems, subassemblies from people. What they've done as the interface isn't necessarily what you expect, which is why we often go, it'd be really, really nice to build this robot with standard parts. Unfortunately, we have to get the circuit boards in the fingers and in the palm, and they just aren't small enough, so we have to shrink it down.
What about people using your robot hands? Would they ever be like plugging them into other things they already have?
So at one level, our robot hands have an EtherCAT connector on the end, basically Ethernet. Talks to your computers, you send it stuff in ROS using the EtherCAT control stack in ROS. All works very, very well for nice and simple, nice and robust. At the other end, actually on the back of the palm of one of our hands, if you look carefully, you'll see a couple of 6-pin connectors. And one of those is basically an SPI port that's designed to take an 8-bit ADC. And the other one is 4 analog inputs with a 5-volt line, so you can power some sensors off it. And the reason for that was people keep saying, can I just get one extra sensor in? And we were like, yeah, here's a connector for it. Just plug your extra sensor into that.
Yeah, that makes sense. So as well as your work at Shadow Robot, you're actively involved in driving national and international policy through your role as one of the SME directors of the EU Robotics Association. So what policy changes would you like to see to help robotics SMEs thrive?
It's interesting. I've been doing this for a long time, and we've said the same thing many, many times to many, many people. And essentially what the challenge for people in robotics is that robotics is not a product. It's a set of tools. So you don't say, I want a robot. You say, I want a clean floor, and you go and buy a vacuum cleaner that happens to be an autonomous vacuum cleaner.
Mm-hmm.
You don't care it's a robot. I mean, it might be a bit of marketing on the box, but frankly, you want a clean floor. You want to manufacture cars, you buy some robots. You assemble those into a production line, or someone does that for you. You have some robots, but you didn't go out to buy robots. So the challenge for us in robotics is that we are a substrate, and we have to turn that into applications and products. And that usually means working with people who maybe aren't quite sure yet what they want to do, and helping them manage the risk of that transition. So it's not quite R&D. It's not quite capital investment, but it will probably need some capital investment. It's certainly somewhat risky. And the problem is that for it to really work, it's got to be done deployed in somewhere that people care about, because otherwise it's a little pilot that people go, oh, that's nice. And then they never, so you've got to use it. So it's how do you de-risk people building a new thing that uses robots to do the job that they're actually trying to get done? When they're like, well, we charge £100 to do this job and it costs us £80 to do this job. If you bring a robot in, the first time we do the job, it'll cost us £500 to do the job. So we're going to lose 400.
Yeah.
So we can't do that. Okay, how do you de-risk that? How do you make it possible for people to try doing their actual commercial problems, their actual real problems, with a new technology that will fail? You have to assume that. At some point it will fail. So you're going to do the thing that you're dependent on with a system that is unreliable. How do you manage that transition? And how do you effectively say, you know what? You can charge for the cost of doing that somehow. You can offset it against tax. You can get a tax credit. You can get an R&D credit. You can get some early stage funding, grant funding to make it possible to do that. And here are some people you can trust to work with to do that. So at the moment in the UK, there's a project around setting up robotics adoption hubs, which are essentially to help with this, to de-risk it, to say, here are some trusted third parties you can go to who can say, I can help you work out how to use a robot to do this. They can't necessarily do the whole job, but they can certainly give you one piece of it, which is someone credible who can help you do that. But then there's also the problem of, actually, if you try doing this stuff, you're going to lose money for a while doing it. So how do you make it possible for people to, effectively, for the finance director to hold their breath for long enough for it to get profitable again? How do you make them comfortable?
Yeah. I mean, obviously it's true that robots break, but humans fail as well, right? Like, you bring on a new employee, they might not do their job very well, or they might have an accident or break something. I guess maybe the investment in a new employee is slightly less than in a new robot, but I don't know, is it as much a state of mind of the way people think about machines versus people?
I think part of it is we're used to the idea that people can hit the ground running at certain things and do many things, but not all things. And if you have specialized skills in your organization that you need people to have, you'll have a training program for that. Because you'll know that we use the Xcode widget. You've never seen one of those before. So on day 1, induction, day 2, Xcode widget training, day 3, now you should start getting some work done. But if you're building a system, and we are talking about building systems here, the problem with that is actually building systems is really, really hard. There aren't shortcuts beyond let's put together a simple thing that works and then make it gradually more complex. And that will require some clever people to be doing it and some time spent doing it. When someone comes along and says, I got a system that just works and you can just turn it on and use it, usually that's not true, unfortunately. Unless it's a very well-defined, very specific problem. If you want to buy a milling machine that can take a chunk of steel and turn it into a nicely machined chunk of steel, well-defined problem, plenty of people can sell you that. 3D printer? Yep. Although even with a 3D printer, if you sit there and look at sort of forums and blogs about it, you find that they're not quite as much of a system. It's more of a tool that works, but needs deep insight into getting the right things to happen from it.
Yeah.
And I say that with the greatest respect to 3D printer developers, because we've had 25 years of this stuff and they're amazing, and still quite difficult.
Yeah. You also mentioned, that robots are not a product. I think that is kind of the opposite of what the humanoid robotics community seem to be pushing at the moment. How do you feel about this kind of proliferation of humanoids?
I think it's an interesting one, because we've known for a long time that robotics hacks people's brains. I don't mean that in a bad way. I mean, if you see a machine moving, then there's kind of an animistic tendency that kicks in, and you start ascribing intentionality and purpose and behavior and reasoning to it. Just because it's doing something, you think, oh, it's doing that. Look at it struggling. Yeah. it's not struggling. It's moving over and over again the same way, but you think it's struggling. And we've seen this for years. We said we build a biped, and people say, "What's his name?" And we say, "We build a robot hand." What's his name? It's a robot hand. It doesn't have a name. It's not a person. But all robots have names. Everyone's robot has a name. Because this is kind of a thing that the human brain does. I mean, if you've ever seen a really good puppeteer, they can pick up a completely random inanimate object and give it life.
Yeah.
Right in front of you. And you're literally looking at this thing and it's like, wait, that was a brick. Now it's not a brick. It's Cyril the brick. Our friendly Cyril the brick.
Yeah.
And so on. And this is it's a good thing for the brain to do. It's a very powerful thing that the brain does. But it does mean that we're prone to this kind of misapprehension that much more is happening inside the thing that looks human than actually is happening in there. You're like, it's a humanoid. Of course, it can do all the things a human can do. No, mechanically, it might be capable of doing all the things a human can do. I don't know. Any particular humanoid may or may not be mechanically capable of doing all the things a human can do. But the software didn't magically jump forward over the last 2 years.
Yeah.
The state of the art in robot control software 2 years ago and today, steady progress, but not, wow, suddenly we can do all the things a human could do that we couldn't do 2 years ago. So I think there's a certain element of you see a humanoid and it just kind of hacks that bit of your brain that goes, oh, I know what this is. I know what that does. I understand it. The best result I've heard about this is from companies where they are trialing humanoids. And when you go and talk to their robotics development teams, you say, so what are you doing with them? And they say, well, the board is very happy that we're developing humanoid robot technology and exploiting humanoid robot technology. You say, developing? They say, yes, look at this humanoid robot technology we're developing. And they point at something and you're like, that's a UR10 with a Robotic gripper on it and a stereo camera. And yes, humanoid robot technology, but now the board will fund it.
Yeah, I mean, I was going to say something along those lines of, it seems like a lot of the hype is mainly geared towards investors rather than customers at the moment.
I mean, maybe it would be kinder to say it's geared to getting attention. And sometimes that's what you want. You say, look, we've got stuff that works. No one's got that we've got this stuff. Oh, here are some proxy technologies that let us show it. And people are like, oh, wow, this is possible.
Yeah.
Oh, okay. You can actually move stuff around in a warehouse with 2 manipulators engaging with it, not just one. Is it worth doing that? You can have something move from A to B and then do a task in both places. Is it worth doing that? And of course, all the people who've been building mobile manipulating robot systems, AMRs with arms on for years are like, hello, we can do this. And it's like, oh, yeah, you can already do that. And, oh, it doesn't fall over. We can do safety standards for it. Oh, we don't have to certify it differently because you've already done that. So I think it's interesting. It brings attention. Yeah. To what extent people are taking advantage of a bubble to do financial investments? Well, I don't know. I'm not in the finance game.
Yeah, fair enough. Rich, it's been lovely speaking to you today. I've been talking to Rich Walker from Shadow Robot Company. Thank you.
Thank you.
Thanks for listening. If you enjoy Robot Talk, please share the podcast, subscribe, and leave a review. And if you've got a question you'd like me to ask one of my future guests, you can contact me on social media at Robot Talk Pod, on Patreon at patreon.com/Claire Asher, or at robottalk.org. I regularly announce upcoming guests on all those platforms, and I'd love to include your questions in my next interview. This episode was produced in collaboration with euRobotics, an international non-profit association that aims to boost European robotics research, development, and innovation. Find out more by visiting eu-robotics.net. Next week, I'll be talking to Chen-Ying Liu from the University of Oxford about origami-inspired robots. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk Season 6 is sponsored by the Hamlin Centre, Imperial College London.